LLM acceleration is possible using today's hardware, and in this talk we're going to go into some predictions on how fast it is using alternative accelerators, so not the typical GPUs you might be used to, but rather more exotic and upcoming hardware, part of which we as Pi3G distribute in Europe. So if you have further interest in this topic and these hardware solutions, please do reach out to us. Without further ado, let's go into the presentation. So for the sake of getting a target token number, I'm using an example where we're looking to be able to talk to, let's say, a car or other appliances and get natural speech output out of it. And how fast is speech? Usually about 150 to 160 words per minute would be the upper range for the output. Conversational range is given between 120 and 150 words per minute. I have some references in this slide for you if you're interested further in this. By the way, speech records may be set, but the speech of these record holders is quite unintelligible. So for our sake, we can calculate that 100 tokens roughly correspond to 75 words. This is true for the English language. For other languages, it might be a bit different. And then we do the simple math of saying, okay, we end up with 150 words per minute times 100 tokens divided by 75 words per token. We are roughly at 200 tokens per minute, which corresponds to 3.33 tokens per second. There's a second part to this, which is the latency. So imagine in this story, two brothers of Häme in Finland were on the way back to work in the morning, or well, on the way to work in the morning. And then one of them said, "Is it here that I lost my knife?" And coming back now, home in the evening, the other asks, "Your knife, did you say?" Imagine leading a dialogue that way. How much information could you transmit and how long would it take? What might work for these two brothers in Finland will probably not work in everyday life. So the time to a response is really important. And there's this interesting study which was done by Stivers et al., which I've provided a link here in the slide if you're interested. And they've analyzed this across different languages. And it turns out there's quite variability across languages. In English, per default, we are at roughly 236 milliseconds average response time, whereas some people like the Japanese seem to be blazingly fast with the responses. Personally, I think they probably interrupt a lot of the time, which you see if there's a negative value here, is this with the Japanese. They don't let the speaker finish their sentence, actually. And the Danish are more on the side of giving slower responses, of maybe taking some more time to process, or basically actually giving the other person the ability to finish their thought and their sentence. In any case, we are targeting an average response time of something like this in order to make it feel natural. So let's say half a second tops is what we want for response to feel like a human dialogue, a flowing, natural dialogue. So if we speak to the car, or we speak to our kitchen appliance, or we speak to the computer or whatever, we do not want to wait for 2 seconds. That would feel too slow for us humans. So there's two phases which correspond to these two different parts. Remember, there's the speed at which the words are being actually produced, the tokens in this case, and there's the speed at which the answer occurs. So the second, the latter one, is the processing the prompt, the prefill. So basically what happens is we have a speech recognition model which recognizes the speech, then translates it into a text string and throws it into the large language model. The large language model now is able to process the prompt. This is called prefill. And this is compute constrained in teraflops or in TOPS because we are able to parallelize a lot of this processing. So we can take the entire sentence or sentences and process them in parallel to create the matrix or the vectors and whatever we need in order to be able to calculate the further results, the answer, the response. The token generation, in turn, the so-called decode phase, is memory bandwidth constrained. The reason for that is we actually, in order to predict one single token, we need to process this with the entire model, and then once we have that single token, we need to append it to the previous result and process it all over again. But we can't parallelize this because we don't know if we try, like we can't try to predict 5 tokens at once, because we need to, the second token will depend on the first, and the third token will depend on the second, and in turn, so it's a chain of dependence. So basically we need to process every one of them in turn. We can't parallelize this process. Okay, there's the caveat, there's different approaches to this, and they are being used, but just roughly at this stage I want to explain. So basically we are memory bandwidth constrained by having to load the entire model once for each token in turn, and we have to load it once for every token, which means that the speed at which we're able to load the model and do the calculations with the loaded values is going to determine the speed at which we can generate the tokens, as we will see. So, as I said, the entire model has to pass through the accelerator of the GPU once for calculation of each token. At a model size of int 8, the quantization int 8 parameter count is roughly corresponding to the models, to the actual size in gigabytes. You can see with the Gemma free models, the different ones which are available, 1 billion, 4 billion, 12 and 27 billion. Roughly we have 1 gigabyte, 5 gigabyte, 14 or 13.3 gigabyte and roughly 30 gigabyte. So roughly, more or less, we need that much memory. We need at least that much memory, first of all, and second of all, we need to run that entire set of tokens through, or like the entire set of these parameters through our GPU or our accelerator at once in order to be able to generate that token. So memory speed matters. It matters a lot for the second phase, the decode phase, which is what most people will perceive as this, model giving output. Why do we accelerate at all? And comparing to why don't we run models on the CPU? So for example, if I use Gemma 3 4 billion instruct and Quant 4, so note this is not even Quant 8 but Quant 4, and with 3.34 gigabytes in size, we will get a tokens per second output rate of 13.28 on my desktop CPU, which is quite powerful. It's a Core i9 with 8 cores. And we will get 68.8 tokens per second on the GPU, which is a GeForce RTX 4060. So this is not a top-of-the-line model, but it's still definitely much faster than the CPU. And the time to first token, remember the slide with the two brothers, is 0.45 seconds for the CPU and 0.2 seconds with the GPU. Again, because the time to first token is compute constrained, and the GPU just has a lot more parallel compute going on, so it can process the data much more efficiently. Why do we use accelerators, specifically compared to GPUs, or generally compared to CPUs? It's not just speed, it's also other things. There's a lower energy usage, a lower cost compared to GPU acceleration. You might imagine GPUs are like multi-purpose tools. So every time you're using it for LLM purposes, you are using something which could be used for many, many, many more purposes. And so it's a more expensive tool. So, for example, it's like a Swiss Army knife, which you're using, versus a screwdriver, which would be a good or a better fit for the job at a lower cost and maybe lower weight as well. Then there's the heat issue. The GPU typically is less power optimized than some of these accelerators, so it will create more heat. Finally, we are able to offload the CPU for other tasks. For example, in our example here, we are trying to speak with an appliance, a car or a juicer or other devices, and the speech recognition could be able or would be able to run on the CPU possibly, or the application logic could run on the CPU. Industrial temperature grade is another major factor. This will of course depend on the vendor of this accelerator, but it's something which NVIDIA may not be able to provide, industrial temperature grade GPUs for certain applications. And automotive certification suitability, depending on, again, on the vendor. Now, the latter 2 points are something where, as I said, like NVIDIA has some offerings, but not every desktop GPU card, let's say an RTX 4090 or something, is automatically industrial temp grade or automotive certified. Another point which I have not mentioned here is that these devices typically are only available for a certain number of years. Now, if you're designing an industrial solution, let's say the juicer or the car we were talking about, you would want a certain guaranteed rate or a guaranteed amount of years of availability of this. And you might not be able to get that from NVIDIA. Some of these other accelerator companies are very aware of this problem, so they are going to provide you fixed and guaranteed number of years of availability on their silicon products, so you can continue to manufacture your devices. Let's get into the actual hardware options, shall we? So I've picked a couple. The market is wider than that, most certainly, and I'm looking forward to your comments. So if you know something which I haven't mentioned on this or the next slide, and you feel this is a good option I should consider and I should be talking about, please drop it into the comments below. Thank you. And while you're at it, you might as well like this video if you have watched so far. It really means a lot. I appreciate it. So, the EdgeCortix Sakura 2, the Axelera Metis, the Halo 10H, and SiMa.AI SoC Modalix. These are alternative accelerators. Non-mainstream accelerators. I'll have some NVIDIA options on the second slide, which is coming up in a little bit, but let's discuss these first. So Axelera Metis is on the market today. Sakura 2 and Modalix, as far as I understand it, are available and sampling to customers as of the recording of this video. And Halo 10H is not quite ready yet. It's available currently for high volume possibilities or options because they still need to tune their models. Nonetheless, we can already say, and we know some details about these accelerators. First of all, maximum amount of RAM. This really matters because of the size of the model you want to fit in. One thing I didn't mention so far is that there's also other things you will need to fit into the RAM. For example, the so-called KV cache. This KV cache is actually a partial computation result of each token generation, and we store this in order to not have to recalculate a lot of these values. This way, instead of the token generation getting slower and slower because we do many more calculations each time a token is generated, it kind of stays at a similar speed, more or less. That means we scale linearly with the length of the output versus quadratically or with a different higher order, exponentially. So you want to be sure that the RAM is actually bigger than the model which you're fitting into it, because, as I said, other things like the KV cache also go into it. In this case, the Halo has the lowest amount of RAM which is available, 8 GB. Metis will be available in up to 16 GB. And right now there's a 4 GB option, where also, by the way, distributors of Axelera. We also work with Halo, and I am personally also able to introduce to the EdgeCortix and the SiMa teams if that is of interest to you. Again, do please reach out if you're looking and working in these fields and looking to design a device. There will be contact data at the end of this presentation. So first step, see how much RAM you need in order to fit your model. Second step, watch the bandwidth. I'm going to go into a calculation as how many tokens per second roughly you can achieve under theoretical limits. and I'm going to say how much practically, what kind of factor you should calculate as a safety buffer. But roughly, the DRAM bandwidth can be calculated from the type of memory technology. With EdgeCortix, for example, LPDDR4X, and with SiMa, it's LPDDR5. Now, if you calculate the bandwidth and you know how wide the bus is, in the case of Sakura, for example, it's 128-bit wide. In the case of Metis, it's 64-bit wide. So because the DRAM is wider with Sakura, basically it means more memory chips are being used in parallel. It can do 68 gigabytes per second versus Metis with 34 gigabytes per second. And as you see, it scales quite nicely. So 32, 64, 128, from 17 to 34 to 68. Now, Modalix is a different beast because it has 128 bits versus the EdgeCortix Sakura, same 128 bits, but it's 102 gigabytes per second and 68 gigabytes per second. Remember, I told you it's the memory technology which also matters. So in the case of Halo, Metis, and Sakura, we are all on LPDDR4, whereas the ML-SoC Modalix is LPDDR5. So data rates are faster per pin or per bit which is transmitted. That is why we are able to achieve up to 102 gigabytes per second on it. One important bit, of course, is how fast interconnects within this Modalix are and whether all of this bandwidth can be actually used for token generation and model loading and so on, and whether the compute engines are fast enough. But for this first observation, we need to pick the right candidates, and the memory bandwidth is one such important factor to consider. Next up, we have the performance. So if we look at EdgeCortix, we get 60 TOPS at int8 or 30 teraflops at BF16. BF stands for brain float. The 214 TOPS of Metis are higher than the 60 TOPS of Sakura, but keep in mind that these accelerators partly were also designed as vision accelerators. With vision, you do not need to load huge models which don't fit into the accelerator itself, but actually you only need to stream video streams and vision data. That is why the accelerator 214 TOPS might or might not be contributing, like basically it might matter less actually how high the TOPS are than the DRAM bandwidth on these chips. So also another point to keep in mind here is that we need to compare the right values to each other. With Metis it's int8, with EdgeCortix also int8 or BF16. With Halo we have int4 in 40 TOPS. So if this was an int8 model which we would load into the Halo, we would have to calculate 20 TOPS if it scales correctly. And SiMa claims 50 TOPS at int8. And then lastly, we have the power consumption, which goes from 3.5 watt for Halo, which is a really low power chip and solution here, to 8 watt typically on the EdgeCortix, and 3.5 to 9 watts on Axelera Metis. Again, keep in mind, some of these accelerators were designed to target more the vision transformer, or not the vision transformer, but the vision market, CNNs specifically, so convolutional neural networks, which means that the memory speeds were not designed to be as fast as what would be useful for LLMs. This is a first generation crop of products here. Okay, maybe second generation could say in with Sakura 2. But the next generation, most likely of all of these devices, will have significantly higher memory bandwidth in order to be able to accommodate those LLM models and to be able to load them faster and to use the compute which they have at a faster rate to be able to saturate that. Another side note for Halo, in this case, I calculated the bandwidth and based it on an estimate by the Micron part number, which Micron provided in the chipset partners list, because Halo currently does not publish this DRAM bandwidth publicly. Now let's come to some other hardware options, notably NVIDIA options. There's the Jetson AGX Orin and the Orin NX. We have a maximum of 64 GB of LPDDR5 or 16 GB of LPDDR5 on these options, and we come to a fantastic DRAM bandwidth of 204 GB per second on the Jetson AGX Orin. This is due to a 256-bit wide bus, so basically it's several of these chips being working next to each other and streaming data in parallel into the Jetson AGX Orin. And it has 64 GB of RAM. It has a great performance at 275 TOPS. That's int 8, by the way. And of course, the Jetson might also be able to do floats if you need that. The Orin NX is a bit slower with 157 TOPS. And on the power consumption side, we see that these devices use quite a lot of power, 15 watts to 60 watts. Now, to be fair, these are way more fully integrated devices than these here. So they have a host system as well. So probably you will not get to 8 watt for the total system design here, or the 3.5 watt on the Halo 10H. Although usually you would use a host CPU, host processor in order to run these devices. I'll get into that a little bit later. Then there's some more exotic options like the Qualcomm QRB5165. That was a device which I was able to get some data on. In this case it has 16 GB of LPDDR5. It's a package-on-package memory solution, and which means the memory goes on top of the Qualcomm SoC. Has a 44 GB per second DRAM bandwidth at 64-bit width and 15 TOPS int 8 performance. Keep in mind that previously people purchased things like the Coral accelerator in order to get 4 TOPS of performance. So the performance which is built into the SoCs, into the chips, is growing, and this performance can also be used to do LLMs. And it's got a decent power consumption of 3.5 to 9 watts. Now that's what I was able to find out about one of the Qualcomm products. For a car appliance, as what we discussed as one of the examples, you would try to use something like Qualcomm Cockpit maybe, or MediaTek Dimensity. With CX1, CY1, CM1 or CV1, unfortunately there's zero data available publicly on MediaTek Dimensity or Qualcomm Cockpit. If you do know a source of this data, please share in the comments below, and I might do a future video comparing these options as well. I'm actually curious about their memory bandwidth, their performance, and their suitability for LLMs. Now we get into the theoretical memory speed limits. Remember, these accelerators all had a certain DRAM bandwidth, so 68, 34, 17, and 204. All of these turn up in this table. I haven't put the specific names of the accelerators to it, but you can skip back in the video and look them up if you're interested. 17, for example, again was the Halo H10, Halo 10H, and 204 was the NVIDIA AGX Orin. At 1 billion parameters, which correspond roughly to 1 GB of model size, we should be able to hit performance of 17 tokens per second on 17 GB per second. So what I do is I divide the 17 GB per second through the model size, and then I get the tokens per second. So how many times am I able to run the full model through the memory, like through the accelerator, through the GPU? How fast is that? With 17 GB per second, and I have 1 GB for the model size, I'm able to do it 17 times per second. So I can copy it once, twice, 3 times, up to 17 times each second. I can push it through the memory. That's what gives me 17 tokens per second. On 204 GB per second, it's the same, but I can do 204 passes of this. 204 GB are able to go through the full GPU per second at 1 gigabyte memory size, model size. If we go up to about 5 gigabyte, then we simply need to divide by 5. So with 17 it will be 3.4 tokens per second, which we'll achieve. With 204 gigabytes per second, we will be at 40.8, and so on. For the largest model, 27 billion at quant 8, 30 gigabytes roughly, we'll see that performance on 17 gigabytes per second will drop to 0.6 tokens per second. So you can roughly estimate if a model were 34 gigabytes in size, you would need 2 seconds in order to run it once through the entire GPU, or through the entire SoC in this case, for it to do the calculations which are necessary. And the model is as big as it is, and all of these tokens are necessary, except in mixture of experts, which I'm going to just say a little bit in a second about. But basically you need all of these parameters and need to do calculations with all of them. So model size really does matter, and memory speed. Memory speed matters a lot. So these CPU cores or GPU cores or accelerator cores might be sitting idle actually while waiting for data to be passed through them. Simply because the data constantly changes. The calculations which they need to do constantly change. You can't cache that because the model is so big, it doesn't fit into the accelerator itself. It needs to be stored on external DRAM. So depending on your use case, you will need to choose the right type of accelerator, the right type of hardware. You can optimize that. Now, 2 or 3 points about this. So the first point is, this is a theoretical memory speed limit, which is based on a very simple calculation of how fast the memory is and how big the model is, and how many times per second you are able to push that model through the memory at optimum speed. In real-world scenarios, this works a little bit differently. So typically, you will have additional things you need to load from the storage, so the KV cache. At very high speeds or very big model sizes, you might also run into some compute limitations, and actually the memory will not be the main bottleneck anymore. That's something which is architecture dependent. I've done a different video on this in the Business Breeze AI channel, which I will link below. You can watch that. I'm talking about DGX Spark and DGX Station, theoretical memory limits, and also about the Mac. So in these scenarios, I've calculated that you roughly, on very high performance hardware, like NVIDIA GPUs, you will end up being about 80 to 85% of the theoretical memory speed limit, which is right like the ceiling which I've seen. The bottom can go quite low, but usually you could estimate it as maybe 50% of the theoretical memory speed limit, that you will be able to achieve that without problems. So the values you get on this slide, you have to take them and divide them by 2. That's the one insight which I have. Second insight is for mixture of experts models. They are actually not using all of the experts at once. So for example, a popular model of this will use 8 different experts, but only 2 of them at once. So you will be loading all the 8 experts into the RAM, so it needs to be able to have enough memory size in order to have all the experts in the RAM. But then you will only be using 2 of them at the same time, so you can divide the model size by 4 and achieve the necessary speed by pushing this. And I think mixture of experts models are a very interesting approach, because they don't force, they work around this memory bandwidth constraint. They're not as efficient as pure models, where you would run the entire model, but they might be just what we need in order to increase quality of the model's response without actually requiring us to invest into even bigger and faster memory chips. And by the way, these memory chips can get quite expensive, and they can get quite fast. So here we're talking 204 gigabytes per second as a top of the line limit. The DGX Spark has 288 gigabytes per second, and DGX Station has 8 terabytes per second. That's 8,000 gigabytes per second. So it uses special memory, but that's a machine which isn't, you could probably not really call it an edge device in the sense which I'm using the edge devices here. Let's compare apples to apples and make another note. So the Sakura 2 is an M.2 and a PCIe card and a chip, as is Axelera Metis and Halo 10H. The SiMa.AI SoC Modalix, on the other hand, is an SoC with an application processor. NVIDIA has system modules including application processors, and Qualcomm Cockpit and MediaTek Dimensity are SoCs including application processors. This means that for designing in Sakura 2 or Axelera Metis or Halo 10H, you will need a host CPU, which will run the actual application, maybe something like the voice transcription, speech translation, or speech recognition machines. And you will outsource the actual model calculation, the LLM calculation, to the accelerator. With MLSoC Modalix, NVIDIA and Qualcomm and MediaTek solutions, you will run everything on one chip or on their module. Depending on that, the price changes, and also, of course, the perception of what you should design into your system or not. Again, if you need guidance on this, please feel free to reach out to us. We're specializing in this field in Europe and are able to provide deeper insights than what I'm able to convey in these few slides to you. I would like to introduce a company to you called Unigen, which is an AI systems partner we've partnered with in the US. They have visual and Gen AI capabilities focused on high performance per dollar and high performance per watt, which typically means using alternative accelerators. Are able to do hot swap and plug and play solutions, have a broad manufacturing infrastructure, SMT assembly, and they have 3 sites around the world, including low-cost sites in Vietnam. They're automotive certified, aviation certified, have certifications like CE, FCC, KCC, VCCI, and VE, and also other locations, as I said. So they have US, California headquarters. For further information, please reach out to us. We are European AI distributors working with many of the companies which I've mentioned in these slides and able to get you in touch with the right partners in Europe, in the US, and around the world. We are Pi3G, we are European AI distributors, and if you want to reach out to us, please use support@pi3g.com. We bring deep technical expertise and have our own software and ML development team, and will be able to support you in all your artificial intelligence needs. Whether it's Vision AI or LLMs on the edge, we have you covered. Thank you for watching this far. If you've come this far, please subscribe to our channel and drop me a comment below what topic you would like to see next. Thanks and have a great day.